This is lesson 24 for 7th grade, and we're going to talk about reducing fractions again. They call this in the book part 2 because it's a little more in depth, and it's also, well, it brings a new strategy for us to use since we've learned some things up to this point that could help us reduce fractions. So, as we know, there are a lot of different ways to reduce a fraction, but we're going to talk about one way in particular today. Alright, so first of all, here's what we want to get accomplished by the end of this lesson. We will want to learn how to reduce fractions by using prime factorization. That's taking our composite numbers. Those composites have more than two factors. Remember, primes are numbers that only have two factors, one in themselves. But composites we can break down into their prime factorization, basically breaking them down into all the prime factors that we can multiply together to get that composite number. We'll show you that in a second again for review. So we're going to reduce that way. And we will learn to reduce before multiplying the fractions. So we're going to reduce before we multiply fractions. This will help save us time and some headaches in the end. If we just multiply straight across, we might get some bigger numbers and not be able to reduce as easily. So this is also known as canceling, and I think we're going to enjoy that a lot because just for the fact that it will help us before we reach the end. Alright, so we've been reducing fractions the normal way. We've been looking at the common factors that the numerator has and the denominator has, and we've been dividing by that common factor. That's not always easy because we're not always sure what numbers are divisible by. And it's also hard to find the greatest common factor, because if we find the greatest common factor and we divide numerator and denominator by that, then we don't have to reduce anymore. But it's kind of like a guessing game sometimes when we have larger numbers. So we'll look at an example like this one, and we'll show you, okay, we look at letter A here. It says we want to use prime factorization to reduce 420 over 1050. Now, right away, it's not easy to come up with, what's going to go into those two numbers that we can reduce with. Except for the fact that we do know that 10 goes into both of them, so that's a good starting spot because they both end in 0. But if we find the prime factorization of both the numerator and denominator, we can make reducing much simpler. So 420, I know that 10 times 42 equals that. 10 is 2 times 5. 42 is 6 times 7. And 6 is 2 times 3. So now we have all these primes. Alright, so prime factorization of 420 would be all of those circled numbers or prime numbers multiplied together. 1050 looks like that's going to be 10 times 105. Alright, and we know 10 is 2 times 5. 105 is 5 times 21, and 21 is 3 times 7. Here are all of our primes. Alright, now when we wrote prime factorizations before, we'd count up how many 2's we had or how many 3's, and we put them to certain powers. So like 2 to the second if we had 2 of them, 3 to the third if we had 3 3's, that type of thing. We're not going to do that this time. We're just going to write them out in order. So we go 420, that's 2 times 2 times 3 times 5 times 7. So 2 times 2 times 3 times 5 times 7. Alright? That's another way to write 420. Now 1050, 2 times 3 times 5 times 5 times 7. Alright, now from there we're going to do what we call canceling, and any of the pairs that we have, top and bottom, we can cancel out. So 2 over 2, that's just 1. 3 over 3, that's 1. 5 over 5. And it looks like, 7 over 7 as well. Alright, so what do we have left? we have a 2 left, and we have a 5 left. So it looks like this reduces to 2/5. So that's one way we could reduce that fraction. Now it says for B, what's the greatest common factor of 420 and 1050? Well, let's look at what they share common-wise. 1, 2. They share a 5. They share a 3. And they share a 7. So if we multiply all those together, 2 times 3 times 5 times 7. So we got 2 times 3 is 6. 6 times 5 is 30. 30 times 7 is 210. Now, if we would have divided each, the numerator and the denominator by 210, we would have come up with 2/5 right away. Because like I said before, dividing by the greatest common factor gets you to that full-on reduced form right away. But how would we have known that 210 was a common factor between these two? We wouldn't have been able to figure that out without our prime factorization. So this is a type of problem when you get some bigger numbers, and obviously there could be much bigger, where reducing with prime factors would be a good idea. So just another way for us to reduce there. Alright. Let's look at this example here. Alright, a set of alphabet cards includes one card for each letter of the alphabet. So we've got 26 letters in the alphabet, which means 26 cards. If one card is drawn from the set of cards, what is the probability of drawing a vowel, including Y? So our vowels here, A, E, I, O, U, and Y. There's our vowels. And we would have how many letters total? 26. That would be A, B, B, C, X, Y, Z. Alright, so on the bottom here we're going to have 26 total. And on the top we have 1, 2, 3, 4, 5, 6. So 6 out of 26 chance that we're going to get a vowel when we draw, but we can actually reduce this, and we're going to reduce it by, if we use prime factors, we can do that, I guess, since that's the topic. 2 times 3, 26 is 2 times 13. So we've got 2 times 3 all over 2 times 13. We cancel out our 2's and we're left with a 3 out of 13 chance that we're going to get a vowel. So a little probability with our reducing there. Okay. So here's where we get into the multiplying and where we're going to want to reduce before we multiply. Okay, we have an example here where they multiply straight across first before they reduce. So 3 times 2 is 6, 8 times 3 is 24. So we get 6 24ths, and we know that if we divide each of these by 6, 6 divided by 6 is 1, 24 divided by 6 is 4, we get 1/4. But we could have made this a little bit easier. We can avoid reducing after we multiply by reducing before we multiply. If we reduce before we multiply, it is also known as canceling. So I want to see if we have this here. Yes. So what we're going to do is look at opposites or diagonals when we are doing this. So 8 and 2, they share a common factor. Their common factor is 2. 3 and 3 share a common factor. Their common factor is 3 that they share. So what we could have done is we could have said, okay, 3 and 3, we'll cancel those out. 3 divided by 3 is 1. Same for down here. 8 and 2. We'll divide by 2, so we get 1 here. If we divide by 8 by 2, we get 4. Now our new problem is 1 times 1, which is 1, and 4 times 1, which is 4. So we're going to go over some examples of this. Canceling saves us a lot of time and energy in the long run. So when we look at something like this, you could go ahead and multiply straight across, but let's notice that 9 and 3, they share a common factor. They actually share, they share 3. 3 can divide 3, and 3 can divide 9. So 3 divided by 3 is 1. 9 divided by 3 is 3. And 16 and 2, well, 2 goes into 16, and 2 obviously goes into 2. So 16 divided by 2 is 8, and 2 divided by 2 is 1. So now we have 3 times 1 all over 8 times 1, or 3/8 for that one. Now we have one with 3 fractions involved, okay? So we can look at any diagonals that would work here. So we're looking at top and bottom separately, but diagonals, of course. Excuse me. Got a bit of a cough. Alright, so let's take a look at 9 and 3 here. Once again, we'll divide by 3 for, excuse me, for both of those. So 3 divided by 3 is 1. Excuse me. 9 divided by 3 is 3. I'm going to take a drink of water. Alright, so our next diagonal, at least the ones that are right next to each other, would be 10 and 5. 5 goes into 10 twice. 5 divided by 5 is 1. 10 divided by 5 is 2. And they're not right next to each other, but 8 and 4 we can do the same thing. Divide by 4 we get 1. Divide by 4 we get 2. So now we have 2 times 1 times 1, which is 2. And 3 times 2, which is 6. And since we got 2 over 6 and we know that that reduces, that means we could have done one more step here before we did anything. So this is 1/3. The one other thing that we could have caught is that after we reduced some of these other ones or canceled out, we still had a 2 and a 2, which we could have done this. So then we would have had 1 times 1 times 1, which is 1, and then 3 times 1 times 1, which is 3. Alright? So if you have to reduce in the end, that means you probably missed something in there, but that's okay. I'm going to check my time quick here. Alright, we are getting there, so I'm going to see what we have left. Maybe we don't have much. Okay. Last example here. Good. Okay, let's look at 27 and 63. They both share 9. We can divide by 9. So if we divide this by 9, 63 divided by 9, we get 7. 27 divided by 9, we get 3. 32 and 20, they both share 4 that they can be divided by. So 32 divided by 4 is 8. 20 divided by 4 is 5. So 3 times 5, 15. 8 times 7, 56. So 15 over 56 there. Alright, that's our last example, and we will be going over quite a few of these on, well, next class period. Thank you.